Welcome, everyone. Today, we are going to explore the journey from propositions to predicates and quantifiers. This is a foundational topic in discrete mathematics and logic, so let's dive right in. Step 1. What exactly is a proposition? By formal definition, a proposition is a declarative sentence that is definitively either true or false, but it cannot be both. Let's look at some real-life examples. New Delhi is the capital of India. This is a true proposition. How about elephants can fly? This is clearly a false proposition. But what if I ask, what time is it? This is not a proposition at all because it is a question. It doesn't have a true or false value. We can also look at set theory examples. Let our fixed set S contain the numbers 1, 2, and 3. The statement 2 is an element of S is a true proposition. However, the statement 5 is an element of S is a false proposition, since 5 is not in our set. Step 2. What is a predicate? Think of a predicate as a template containing one or more variables. By itself, it has no definitive truth value. It becomes a proposition only when specific values are substituted for those variables. For a real-life example, let P of x be defined as x is a planet. If we substitute x with Mars, the statement becomes Mars is a planet. The result is true. But if we substitute x with pizza, the statement becomes pizza is a planet, and the result is false. In set theory, let's set S be 1, 2, and 3. We can define a predicate E of x as x is an element of S. Also, it is important to note that the number of blanks or variables like x that a predicate has is called its arity. Step 3 involves logical connectives. These are our building blocks, and we will use them to combine statements. First is AND. An AND statement is true only if both sides are true. Next is OR. An OR statement is true if at least one side is true. Then we have NOT, which simply flips the truth value. True becomes false, and false becomes true. Next is implies. This represents an if-then statement. An implication is only false when the first part is true, but the second part is false. Finally, we have the biconditional, or if and only if. This is true only when both sides match, meaning both are true or both are false. Let's look at a predicate with arity 1, also known as a unary predicate, meaning it has one variable. Let's set A be 1, 2, 3, and set B be 3, 4, 5. We define a unary predicate P of x as x is an element of A and x is not an element of B. Let's evaluate this. First, we substitute x with 1. Our statement becomes 1 is in A and 1 is not in B. Logically, 1 is in A is true and 1 is in B is false, so we have true and not false. This simplifies to true and true, so our final result is true. Now, let's try substituting x with 3. Our statement is 3 is in A and 3 is not in B. Logically, 3 is in A is true, but 3 is also in B, so that part is true as well. Our logic becomes true and not true, which simplifies to true and false. Therefore, the final result is false. Next, let's examine a predicate with arity 2. This is a binary predicate which uses two variables. Let's set S be 1 and 2. We define a binary predicate using the implies connective. Let R of x, y be defined as x is in S implies y is in S. For our first evaluation, let x equal 1 and y equal 2. Our statement becomes 1 is in S implies 2 is in S. Logically, this translates to true implies true. The final result is true. For our second evaluation, let x equal 1 and y equal 5. The statement becomes 1 is in S implies 5 is in S. Since 1 is in the set but 5 is not, this logically translates to true implies false. Because the first part is true and the second part is false, the final result is false. Let's look at another binary predicate example, this time using if and only if. Let's set E be 2 and 4. We define m of x, y as x is in E if and only if y is in E. Remember, for this to be true, both sides must match. If we substitute x with 2 and y with 4, the statement is 2 is in E if and only if 4 is in E. Both 2 and 4 are in the set, so logically we have true if and only if true. Because they match, the final result is true. Now let's substitute x with 2 and y with 5. The statement is 2 is in E if and only if 5 is in E. 2 is in the set, but 5 is not, so logically we have true if and only if false. Since they do not match, the final result is false. Moving on to arity 3, we have a ternary predicate, meaning 3 variables. Here, let's use one element variable, x, and 2 set variables, a and b. We defined a ternary predicate using the OR connective. Let T of x, a, b be defined as x is in A or x is in B. Let's evaluate this by letting x equal 4, set A equal 1 and 2, and set B equal 2 and 4. Our statement becomes 4 is in the set containing 1 and 2, or 4 is in the set containing 2 and 4. Logically, the first part is false, but the second part is true. So we have false or true. Because at least one side is true, the whole statement is true. Step 4 introduces quantifiers. So far, we have turned a predicate into a proposition by substituting a specific value. Quantifiers give us a second way to do this. They allow us to plug in a whole set at once. There are 2 main quantifiers. The first is the universal quantifier, which means for all or for every. For a universally quantified statement to be true, the statement must be true for every single element in the set. The second is the existential quantifier, which means there exists or for some. For this to be true, the statement must be true for at least one element in the set. Let's evaluate a for all statement. Let our test set S be 1 and 2. Let's test if every element in S belongs to set B, which contains 1, 2, and 3. Our statement is written as, for all x in S, x is in B. To evaluate this, we must check every element in S. First, we substitute x with 1. The statement is 1 is in B, which is a true result. Next, we substitute 2 with x. The statement is 2 is in B, which is also true. Logically, since it is true for x equals 1 and true for x equals 2, the final quantified proposition is true. Now, let's evaluate a there exists statement. Let our test set S remain 1 and 2. Let's test if at least one element in S belongs to set C, which contains 2 and 4. Our statement is written as, there exists an x in S such that x is in C. To evaluate this, we just need to find one element that makes it true. If we substitute x with 1, the statement is 1 is in C. This result is false. But if we substitute x with 2, the statement is 2 is in C. This result is true. Logically, since we found at least one true instance, which happened when x was equal to 2, the final quantified proposition is true. Let's summarize how we create propositions. A predicate acts as a template with blanks. For example, P of x is defined as x is an element of the set containing 1 and 2. Substitution works by filling the blank with one item, such as P of 1, which evaluates to true. The for all universal quantifier acts like a giant AND statement applied over an entire set. The existential quantifier acts like a giant OR statement applied over an entire set. Ultimately, by either substituting a specific value or applying a quantifier to a unary predicate, you transform that open template into a definitive logical proposition.